Hi everyone. We're going to start probably one of the most important rules that we work on, and that is the chain rule. So we've worked on specific functions, and we do have a couple more to go, but we've got most of them. So we know what to do with power functions, exponential, trig, and we know what to do with some combinations of those. So we know what to do if we've added or subtracted two of them, if we've multiplied or divided. But one of the biggest ways that we use to combine functions is composition, and we haven't really tackled that at all. So actually all three of the first 3 pages of this thing are your preview activities. So I really want you to pause, and I want you to look through. These are basically a whole bunch of examples. I've given you the derivative, and I want you to see if you can spot the pattern, and then use it to make a guess for these bottom 3 blanks that I know you can't see right now. And then come back, and I'll point out the things that I hope you saw. So really important that you see if you can spot these patterns up front. So please make your 3 guesses before you watch through all this. Okay, so this first one actually looks kind of funny. If we take the derivative of x to the 5th, we know we get 5x to the 4th, but there's an extra 1 out here. But hopefully, as you've looked through, this has become clear. So what's happening is, in the original function, every single one of them has this 5th power as the big operation, the last thing happening. But what's getting raised to the 5th keeps getting more complicated. So at first it's just a basic power function, but then it's 2x raised to the 5th power, and then it's x squared raised to the 5th power, and so on. So the inner function changes every time, but it's always getting raised to the 5th. So over here, the derivative, we always see the 5 out in front. We always see the 4th power, and that hopefully looks like a power rule to you. If we have something to the 5th, we go at 5 times something to the 4th. What you should see getting raised to the 4th is always the exact same function that we started with on the inside. And then out here, what I hope you've spotted is that this number is the derivative of this inner function. Derivative of x is 1, derivative of 2x is 2, derivative of x squared is 2x. And so on. So all of these should be the derivative of the thing in the parentheses over here. Which means, and don't forget, these are all examples, so as you go back, yeah, I just kind of wrote them down for you, but as you go back and you're trying to work on homework, if you're looking for more examples, you can look at all of these to try and follow along and see how this works. Okay, so here we have stuff to the 5th power, and hopefully what we've spotted up above is that we should have 5 times stuff to the 4th power, and then we should be multiplying by the derivative of the stuff in the parentheses. So we'll drop the 8 down in front. 7 times 8 is 56. The new power is going to be a 7. And then the derivative of 6x to the negative 3 is going to be negative 18x to the negative 4. So that's what actually goes in the first blank. And then the second one, we once again have stuff to the 5th. This time stuff is a quotient. But up above, we should be spotting that we'll still have all this exactly as it appeared. And then we'll do a power rule 5, stuff to the 4th. And then we need to multiply by the derivative of the e to the x divided by x to the 4, which is going to be a quotient rule. So we'll do the bottom, x to the 4, times the derivative of the top, e to the x, minus the top, e to the x, times the derivative of the bottom, 4x cubed, over the bottom squared. X to the 4th squared is an x to the 8th. And I don't care if you're simplifying these, I just want you to see the pattern and apply it. Okay, and then the last one asks us to generalize. So in general, if you take a function and raise it to the 5th power, it appears that the derivative is going to be 5 multiplied by the function to the 4th power, and then you multiply all of that by the derivative of the function. Okay, so there is page 1. So again, if you want to pause and look, there's not quite so many to look through. The examples are at the top, and then see if you can generalize. Please make your 3 guesses before you watch me work through this. It's okay if you have to change them, but it's really good learning for you to try and guess. Okay, so this time I use the other notation. I'm not using the dy dx, I'm using the ff prime. So my function, what I see is that in every single one of these functions, I have sign of stuff. And the stuff changes, but it's always sign of something. So on the other side, in the derivative, I notice that I always have a cosine showing up, and then the stuff inside the parentheses for the cosine is exactly the same as what was inside the parentheses for the sine. So we have cosine of that same inside thing, and then what's showing up out here at the end in the second set of parentheses is the derivative of what was in here. So if we want to generalize that down to the bottom, if we have sine of 7x to the 17 minus e to the x, looking at the pattern, I think I should end up with a cosine of that exact same thing, 7x to the 17 minus e to the x, and then I should multiply, and in the second set of parentheses, I should have the derivative of this. Oh, I hate when I give myself big numbers. What is that going to be? 70 and 49? 119? Don't hate me if I did bad arithmetic. I think it's 119, but I might be lying to you. And then the derivative of e to the x is still e to the x. Okay, so there is my guess for that first one, and that is in fact right. So that's what you should end up with. No problem if you didn't. This is all about just trying to guess the pattern. Sometimes you can learn more from seeing where you went wrong than just getting it. Okay, second one again is sine of something. So we're going to get cosine of that exact same something. And then we're going to multiply by the derivative of the stuff inside the sine. So that's a quotient rule. We're going to have the bottom, 5x to the 4th, times the derivative of the top, e to the x, minus the top, e to the x, times the derivative of the bottom, 20x cubed. And that's all going to be over 5x to the 4th squared. Make sure you square the 5. It'll be 25x to the 8. Okay, and then the last one is just asking again for you to generalize. So in general, what do you think the rule is if you have the sine of a function? So again, we know what to do if we have plain old sine of x. The question now is, what if it's not just x in there? And the answer is you should get cosine of that exact same function multiplied by the derivative of your inner function. Okay, so there's page 2. One more to go. Same idea. Please try and make your 3 guesses. Look at the pattern, make your 3 guesses before you watch me go through this. Okay, so this one I changed it up a little bit. What's the same every time is the 3x to the negative 1 plus cosine x. So first I have the square root of that. So the big operation here is the square root. If I plugged in numbers, the last thing I do is square root. Here the big operation is negative 6th power, and here the big operation is e to a power, e to the stuff. And the stuff stays the same throughout, so actually it's the inner function that's always the same, and the outer function is changing. So if we look over here, what we should see is that this is that exact same inner function. Let me see if I can find the right thing to underline. Showing up in every single one, and this shows up in every single one, and it happens to be the derivative of this inside stuff. Negative 3x to the negative 2 minus sine x is the derivative of the inside stuff. So if we're looking at the rest, in this first one, the rest is a 1/2 and a negative 1/2. Here it's a negative 6 and a negative 7. Here it's just e raised to that stuff. What I hope you spot is that that's the derivative of the big operation, the outer function. So stuff to the 1/2 power is a square root, which means its derivative is 1/2 stuff to the negative 1/2. Here negative 6, you're seeing a power rule, negative 6 to the negative 7. And e to the stuff is its own derivative, so you're seeing that show back up. Okay, so if we try and generalize, down here we have that same 3x to the negative 1 plus cosine x, now it's to the pi power. So what I see up above says, first, how would you take the derivative of x to the pi? And the answer is you drop the pi down in front, and then you'd have the new power be pi minus 1. So we apply that derivative, but the thing inside, we don't touch at all. It stays exactly the same. And then we're supposed to multiply by the derivative of that inside stuff. So we do eventually take its derivative. It's just in a secondary step. That's the chain part. Chain out the derivative of that. Okay, so now we have that same inner function. The outer function is a sine. So the derivative of sine is a cosine. And we should leave this exactly as it is. And then the derivative of the inner stuff is that same thing I've seen all the way down. Okay, and now we're asked to generalize what we've just been doing on this page, and then we actually have one more here where we put it all together and make a really big generalization for all 3 pages. So in general, if I'm trying to take the derivative of a function of 3 to the x minus 1 plus cosine x, what I'm seeing is I should take the derivative of the function, but not mess with the 3x to the negative 1 plus cosine x. But then once I'm done with that, I should multiply by the derivative of the inner stuff. Okay. So that's what we would say in general if the outer function is changing, but the inner function is something we already have figured out. That's how that looks. And now we're supposed to say in general, if you have any old composition, a function of a function, what do? And what I hope we get to here is you take the derivative of the outer function, evaluate at the inner function. So don't touch g in this step. And then you chain out, multiply by the derivative of the inner function. So you should only be taking the derivative of one function per step. Okay, so this is our proposed chain rule. And I'm going to go ahead and stop this long video here, but I will show you that that actually works in the next one, and then we'll do some examples. Thanks for watching.